Good morning everyone, and welcome to this presentation about standards in the AMI sector. My name is Tony Field and I'm here representing ESMIG. For those that do not know, ESMIG represents European companies that provide products, information technology and services for multi-commodity metering, display and management of energy consumption and production at consumer premises. These products and services enable better outage detection, customized tariff and accurate bills, a precise overview of consumption and manageable demand. Therefore, they help in making energy cleaner, more affordable and more reliable. In my day job, I work for Itron and have done so for the past 20 years, 15 of which I've spent participating and leading various standards, technical committees and management bodies within SDOs and SSOs in the UK, Europe and internationally. Today I'm going to give you a glimpse of the world of standards, how they are made, what they are used for and why they are useful. In particular, we will focus on the segment of communication standards used in smart metering and smart grid applications, which should set the scene nicely for the subsequent presentations on specific projects. So before we start, what is a standard? According to the British Standards Institution, a standard sets out an agreed way of doing something. It's a statement of good practice designed to make things better, safer and more efficient. Standards can cover a huge range of organisational activities, from making a product to delivering a service or creating a process. A standard is a collaborative and collective work. It represents the consensus of a group of experts and other people with an interest in the subject matter. Now, according to IEC, a normative document developed according to the consensus procedures which have been approved by the IEC National Committee members of the responsible committee in accordance with Part 1 of the ISO directives. That's a very formal definition, but of course there are various routes to standards and interoperable specifications, which we'll touch on later, but ultimately the attributes of a successful standard, such as consensus between multiple interested parties, robust processes and procedures, are common regardless of the route to publication. In terms of what a standard is and it isn't, it's obviously a collective work as we've discovered. It's a statement of good practice. A standard is not a regulation or legislation. It's not a legal requirement, although some standards can be used to demonstrate compliance to legislation. It's certainly not the only way of meeting a set of requirements, and it's not about a single implementation either. All specifications start with a problem and an idea and can be elaborated in many different ways. To start with, we have internal specifications, which are obviously proprietary. They're faster to develop. There's no or very little consensus needed, and they result in a single source or licensed technology. Obviously, they're harder for outside parties to influence and participate in the development of such specifications. Next, we have consortium specifications developed and published by a standard setting organisation or SSO. Normally, these are not-for-profit, membership-based consortia that anyone can join. Sometimes there are levels of membership giving differing rights as to the influence on the specifications. Next, we have national, regional or international standards published by standards development organisations. These are formal institutions, and you get representation to those through associations and trade bodies, or you can also attend as independent experts to influence the standard development process. International and regional SDOs are participated in by national representatives nominated by national standards bodies such as BSI, DIN, AFNOR, etc. And then last of all, we have open source standards and projects. And anyone can contribute to these for free, anyone can use them for free and use them with attribution. Whatever you add to the works, you must also make available for everyone else to use. This isn't an exhaustive list of the ways in which standards can be developed, but they're just an overview of 4 common ways in which they are developed. So far, we have mentioned a number of routes to standardization, and this slide shows some of the features of SDOs and SSOs. It's not prescriptive, and there are exceptions to these features, but generally speaking, the major SDOs, such as SEN, SENELEC, IEC and ISO, all require membership via country. National standards bodies are the members, which then nominate experts from the industry to represent the national interests. SDOs focus on writing standards via very well established and quite rigid processes, bringing the largest possible breadth of consensus within their purview. SDOs do not generally involve themselves with the business of certification or testing against the standards. SDOs are very large organisations with huge scope and many technical committees focusing on smaller, more tightly controlled scopes of work. For example, IEC has around 210 technical committees and subcommittees, which in turn have over 1,500 working groups, project teams and maintenance groups. The SDOs mentioned above, and certainly the National Standards Body members, generally require that participants bring with them a wider view than a single company, such as from a trade association or an industry group. The SDOs do not generally charge to participate in the work, but finance themselves through sales of standards. Within the European SDOs, ETSI is a slightly different model, whereby it does not charge for its standards and makes them freely available, but instead charges companies to participate in the standards development process. Now, SSOs also produce standards and specifications, and almost always charge for membership at the company level. They have a very narrow scope and are generally self-financing through membership dues. SSOs generally have marketing budget to promote their standards and specifications, and sometimes SSOs have a close relationship and liaison with SDOs for publication of their standards. SSOs normally have a faster development and maintenance cycle for their specifications and standards, and in many cases SSOs produce specifications that are based heavily on published standards from SDOs and make choices and reduce options in generic standards to provide interoperability specifications. SSOs normally also provide testing and certification platforms for their specifications and may also provide certification and quality marks along with the issuing of certificates of conformity or compatibility. So now we know how standards get written, but what about why they get written? Well, there are many drivers for writing standards. Sometimes these come from standardisation mandates laid down by the European Commission. Things like M441 for smart metering or M490 for smart grids. And this is where work is identified that needs some technical bolstering. So the European SDOs are given the opportunity to standardise and make up the gaps where there aren't currently standards for particular subjects. There are country proposals and needs that are brought to SDOs via the country representatives. There are changes in legislation where new and updated directives require new standards in order to prove conformity with those directives. Sometimes there are company proposals and a desire to create an ecosystem, generally within SSOs, and there are consensus-based market needs where everybody identifies that there's a particular need for a standard and a consensus process is set up to develop such a standard. More often than not, there's always a need for interoperability to open markets because standards create interoperability and allow for interoperability between implementations. So we've looked at various processes for creating standards. Now let's take a closer look at some of the standards that are used in AMI projects. There are many standards used in AMI products which range from the top level horizontal standards covering the general product matters such as safety, EMC, performance, etc. Moving to the next level, there are product specific standards covering form factor, performance, hardware specifications, IP rating, material specifications, etc. Product specific functional and legal metrology standards including the measurement and accuracy of electrical energy and electrical performance. Lastly, but by no means least, we get to the communication standards that are produced by many SDOs and SSOs. The last section in this diagram is elaborated a little more than the others above because as of recent times it's spoken about more and is critical when talking about interoperability between products and systems. Many standards have been used for smart metering over the years, and this shows a sample but by no means all protocols that have been used for communicating with smart meters. Some standard suites provide entire top to bottom stacks such as MBus and Zigbee Smart Energy, whereas others such as DLMS COSEM provide a universal application layer that can run over pretty much any lower layer standards. They have also been used in combinations for various reasons, and in some rollouts wireless M-bus is used to communicate with water and heat meters, but it's also possible to use DLMS COSEM over the top of M-bus. Similarly, in some markets, such as Great Britain, Zigbee Smart Energy is used to communicate with other devices on the HAN, which is the Home Area Network, while allowing DLMS COSEM to be tunneled over Zigbee Smart Energy from the COM sub to the electricity meter, allowing end-to-end communications between third parties and individual devices in the field. Looking a little closer at interoperability, this slide shows various levels of interoperability from the bottom with proprietary specifications produced by individual companies, where there is no interoperability outside the specification owners and those they choose to work with. The next level up is where devices can speak the same language, but maybe not necessarily support all of the same features and functions. This level is controlled either by an SDO or an SSO, but provides the baseline core specifications and standards. These baseline standards sometimes contain more options and choices. Standards with many options and choices do not make it easy the task of interoperability. Right at the top, we have companion specifications that specify exactly what functions and features from the core standards are required to make an interoperable product. This companion specification is normally also accompanied by a test specification and a certification platform to prove compliance. This is normally owned and managed by an SSO. If we move up from the purely smart metering domain out to the larger utility domain, we can see that there is also a higher order of compatibility to consider, where protocol standards used to talk to smart meters must map to and integrate with other protocols used within the ecosystem. This slide shows the relationship between some of the standards commonly used in the utility domain, starting at the top with the Common Information Model, or the CIM, and its relationship with distribution automation and substation control, right down to the smart meter through a suite of standards that are interrelated, providing a consistent representation in supervisory systems of the data structures and control functions of all assets in the field. If we move to a still wider notion of interoperability, we start to look at applications beyond the metering domain into smart cities, smart homes, and energy management systems, assets and applications. The EU Smart Grid Task Force has been running for many years now, first established to advise the European Commission on matters relating to smart grids and ultimately to help draft legislation relating to interoperability of smart grids, in the same way that the Coordination Group for Smart Meters was set up to help advise the EU-wide rollout of smart meters. One part of the Smart Grids Task Force, known as Expert Group 1 or EG1, is made up of representatives from all EU stakeholders involved in the energy industry, and it produced 2 reports on interoperability of smart meters, the first report on functionalities of smart meters and the second on the interoperability of interfaces, which have helped pave the way for later works that are ongoing today. Subsequent to the publication of the Clean Energy Package and the Electricity Directive, Expert Group 1 is now working with the Commission to define further the interoperability requirements for various smart grid functions and processes. This next level of interoperability will be defined in implementing acts derived from the Electricity Directive, starting with metering and consumption data, moving on to demand response, the data required for customer switching, and finally other new services. The first part on metering and consumption data covers a scope of 2 parts: historical, validated data that the consumer must be allowed to access and share via some means such as an online portal, and this would be typically interval data, such as you could be sharing with other third parties for energy switching or some other purpose, but mainly so that the consumer can be aware of their consumption. And this data comes from the metadata responsible party who has downloaded data over the AMI channel and then is providing it back by some means. Now the near real-time data is a much finer resolution data, and it's coming straight from the meter in a much shorter time scale, and that's provided by what's known as the H1 interface. Now the H1 interface is a local interface on the meter that provides a standardized protocol interface for the provision of data. And this goes directly to a consumer device where they can do with it what they will, to observe it, input it into some other system, or share it with some other party. So thanks very much for your time this morning. I hope you find this whistle-stop tour of the AMI standards environment useful. I'll now hand over to my colleagues for their presentations and look forward to speaking with you all later in the panel session.
Good afternoon, everybody. Today I will talk about Flexity, which is a pilot project in which Tico, Engie, Voltalis, Jetlix, Fluvius, CGI, and Elia investigated and tested residential flexibility in Belgium. We investigated how we can use intelligently the digital meter to settle participation of balancing services for appliances behind the digital meter, such as heat pumps, accumulative heaters, and electrical cars. To start off with, first some context as an introduction. The transition of the electricity system is one of the major challenges of the century. The switch towards a decarbonized society brings fundamental challenges for the electricity system, and Flexity believes that the end consumer will play a central, pivoting role to make this happen. Digitalization will be the catalyst that makes the link between the energy transition and this end consumer, enabling that this end consumer can lower its energy bill, increase its comforts, and benefit from the technological investments they made in solar panels, heat pumps, boilers, or batteries. To make this happen, we need a shift in paradigm, where today the center of the system is still largely focused around the centralized generation units with limited digitalization, with limited communication between different voltage levels. There tomorrow we expect that more variable and renewable distributed energy resources will need to be managed properly, and in order to do so, we need flexibility from all voltage levels to maintain a safe electricity grid. In order to do so, we will need to have demand following generation. For that, Elia puts forward three principal building blocks. First, an upgraded market design. Such a market design enables consumers, either alone or via an intermediate service provider, to optimize their electricity consumption by following certain market signals and benefit from it. This can be enabled by, for example, simplifying the access to electricity markets and evolving current communication and metering requirements to enable the participation of low voltage appliances in our current flexibility markets. Secondly, open data access, allowing new consumer-centric services to be developed by new players. First, consumers must be empowered to make their data accessible to third parties to enjoy new services. And secondly, data should be available in a secure and standardized way so that service providers can build these new services. Finally, we need to also have, of course, new digital tools and infrastructure to make this happen. When we look, for example, to the mobility sector, having an open market and standardized communication standards in place is one thing, but also the charging infrastructure and digital tools such as blockchain and artificial intelligence needs to be in place. For instance, to facilitate a fluent settlement of the services that are delivered to the grid. These building blocks are developed together with the market. Elia, together with the DSOs in Belgium, have put in place a new kind of ecosystem in which all market parties are invited to develop new ideas around specific topics, such as flexibility, e-mobility, etc. And out of one of these workshops, the IOFlexity Consortium and IOFlexity ID was born. The overall mission of Flexity was to find an innovative approach to empower end consumers to participate in the energy transition. In general, Flexity had two objectives. First objective was to test which household assets, such as electrical vehicles, boilers, heat pumps, can technically be operated and be used to create value to the end consumer, while leaving in place the existing commercial communication setups, for example, reusing the manufacturer's cloud to operate these assets, and then finally, of course, operate these household assets without loss in comfort. Secondly, and this is definitely also very interesting in the context of this conference, is to test to which extent we can put in place reliable data streams and a settlement mechanism to enable participation of these households' flexibility appliances in the balancing and the wholesale market. Basically, what did we do was we had the digital meter. We collected data from the commercial P1 port of the digital meter. We collected high granular data from this port, and we cross-checked this data with the commercial data flows that we received from commercial parties such as Tico, Jetlix, Engie, and Voltalis. This enabled us to validate whether or not these commercial data flows are accurate and authentic and can be used to settle the flexibility services. Different types of results were obtained. I will quickly go through the different conclusions with regards to the technical feasibility of operating these household assets, also see what's in it for the end consumer, and then I will try to put more emphasis and a little deep dive on the cross-checking methodology and the exact usage of the digital meter, and see to which extent data from this digital meter was used to settle flexibility services of behind the meter appliances. Flexity tested two distinct ways to operate residential flexibility. First way was we installed communication gateways together with steering devices to operate heat pumps, to operate accumulative heaters. Secondly, we reused the existing connectivity of the asset, specifically electrical vehicles, which come with a default connectivity via the OEMs, so the manufacturer's cloud. Not only is this becoming a popular approach for electrical vehicles, but also for residential batteries and for PVs. Secondly, what drove the consumers to participate in the Flexity project? I think it's what we typically see for pilot projects. Participants are driven by a general interest in digital monitoring tools and, of course, the financial savings that they bring along. And contributing to a greener and sustainable electricity system is often also important, but for these, let's say, tech savies, was not considered the most important parameter for participation in this small scale proof of concept. Technically speaking, valorization across different value streams. So what we see, EVs, they can be operated across wide variety of value streams. You can shift charging sessions towards the night. Secondly, also optimize then during the night these charging sessions in function of wholesale prices. And then finally, let's say the cherry on the cake, optimize them in function of participation in the balancing market. Where for accumulative heaters and heat pumps, the main focus was balancing and wholesale market optimization. When it comes to data exchange, we observed quite some compliance issues when these household assets want to participate in the current balancing market. Definitely for appliances that come with this integrated connectivity, we see, and there's still quite some open questions to which extent they comply with the current metering requirements. And now the dongle prototype and really what uh, what did we develop and how did we collect the data from the digital meter? We developed two dongles. We first went for the collection of P1 data, and then we also did some experiments to collect S1 data. So collection of P1 data, there we did a local collection of P1 data of the commercial port of the digital meter, and we published this to our real-time communication platform. There we saw that, well, the fact that we collected this data on a second basis and pushed this data to our real-time communication router, let's say, having this data on a second basis continuously available with good quality is quite a challenge. Secondly, when you look at S1 data, there we saw that the collection was possible, of course, locally, but the processing and the communication came with significant challenges because of the high amount of data. And then finally, cross-checking methodology. This I will do a deep dive in the next slide to show how we can obtain a reasonable insight on the probability that that the overall commercial submetering data that we received from these individual parties in the pilot project was indeed authentic when we only take a look at the digital meter and the collection and the collected P1 data. So maybe very quick, what were our two main research questions? First, can we visually basically identify an activation of a submetered asset, for instance, a car, a heat pump, when only looking at data coming from the access point? And then secondly, can we have an insight on the probability that this data from the access point, we call it here the commercial submetering data, and can we have an insight that this commercial submetering data is authentic and that we can trust this and that we can use this for the settlement of the grid services? And here we have two main findings when we looked at a wide variety of different data sets. Is first, we see that changes in activity on the asset. So when we activate an asset for flexibility purposes, they can, quite honestly, can be can easily be traced back when looking only at data coming from the access point. But of course, when you do this on a manual ad hoc basis, this requires quite some work, and this definitely has its limitations. However, important remark is also that we see quite a strong influence of PV production, which definitely makes the exercise more difficult to make sure and to distinguish to which extent a certain activity can be attributed to a specific asset. So maybe a small word on the methodology that was used. Basically, you can split it up in 3 steps. So first, we identified the base load, and we considered the fact that the base load is considered equal to the overall offtake of the household right before the asset is active. So if we want to validate the data coming from the heat pump, we consider the whole household consumption without the heat pump, and we say this is the base load of the house without the heat pump in question. And secondly, what you do is we subtract this constant base load from the raw P1 data, and what you do is, at that moment in time, you reconstruct a curve that should approximate the heat pump data in question. And then finally, you compare both data sets, being the reconstructed P1 curve that should basically be close to the real physical measurement of the heat pump in question. And then secondly, of course, you compare it with the actual measurement of the heat pump. And this allows you to see to which extent the data coming from third parties, coming from commercial parties in the system can indeed be used for the settlement of grid services. So, a small example that might clarify things. So, when we see at a typical EV, and the figure on the left, you see the blue line, which represents the household consumption as a whole. The orange line, specifically the EV. And then at the right figure, you see the blue line, which is now the reconstructed P1 curve. So it is basically the original data coming from the access point minus the base load that was calculated right before the EV was active. And then you compare this blue line with the actual consumption of the car, which is the orange line. Now, what you see is we took several parameters to see to which extent both lines and both curves are in line. And in general, a cost check definitely has the potential to provide us with a reasonable insight, at least, that commercial submetering data that we receive from third parties is authentic or not. And that this data can also be used to settle our grid services. So I want to thank all of you for your interest. You can keep following our progress, our key findings on the LinkedIn page. And in case of any questions, feel free to contact me at any time. Thank you.
Hello to everybody, my name is Andreas Thaler and today I'm going to present you the second generation smart meters for the electricity sector in Italy. First of all, let's say a short historical overview over the usage of smart meters in Italy. The transformation of the European electricity sector started about 20 years ago, and Italy was one of the first European countries to embark nationwide deployments of smart meters. The mass rollout of the so-called first generation smart meters was between 2001 and 2006. The main advantages of these meters were that the DSOs were enabled to read out and to manage the meters from remote. And as a result of the remote activities, the DSOs were able to reduce their internal costs. The first generation smart meter are embedded in a bidirectional data stream. Information sent from the smart meter via power line communication to the concentrator and in aggregated form via mobile network to a central system. In over 95% of the cases, the meters can be reached and the DSO gets a result for his request. What was once a state-of-the-art technology solution is now approaching the end of service. The technical lifespan of the meters and communication devices is about 15 years. Therefore, the devices deployed during the mass rollout between 2001 to 2006 will soon need to be replaced. The major network operator in Italy, E-Distribuzione, has already replaced about half of the first generation smart meters with second generation smart meters. Second generation smart meters, a technological upgrade. The most important difference to the first generation is the augmentation of the data resolution. Now are available quarter-hour load curves for each point of delivery. Further advantages are the faster response time for actions, for example, the change of the energy supplier, and the easier access to nearly real-time data for customers is also one of the most important things. This data availability increases the consumer awareness to active demand, and it supports also the advanced management of the power grid. Like we have seen for the first generation smart meters, also the second generation smart meter is embedded in a bi-directional data stream, but now with the open communication protocol. The smart meters sends the information through power line to the concentrator. The main difference is that for passing the data from the concentrator to the central system now can be used optical fiber or 3 or 4G connections. So now let's get a quick overview about the system architecture of the second generation smart meters. The second generation smart meters have two separate channels of communication, chain 1 and chain 2. Chain 1 for the communication with the central distribution system, and chain 2 for customer energy management systems, the so-called in-home devices. Chain 1 uses the A-band of the power line communication and as a backup the 169 MHz radio frequency. Chain 2 uses the C-band of the power line. From a system perspective, one of the main changes in order to the first generation meters is the introduction of dual power line communication and radio frequency communication. Chain 1. How already said, chain 1 uses the power line communication A-band. This technology is already widely used, known for the communication robustness and for the optimal cost-benefit ratio. Also, the communication through the 169 MHz frequency, in our case only used as backup, is widely used. In Italy, for example, for the remote management of gas meters. Chain 2. Chain 2 uses the PLC C-band with a dedicated communication protocol that enables stakeholders to develop devices and services that can interact with the second generation smart meter. So the Chain 2 data will be available nearly in real time to the customer. In the case the customer allows it, the data will be also available for retailers or providers of energy services. This could enable a continuous grid quality of service monitoring. That real-time data also enables the development of new offers, for example, prepaid offers or flexible rates. It enables also the monitoring of the energy footprint for each point of delivery. So now we have reached my last slide for this presentation, the rollout plan for the second generation smart meters. The distribution system operators have to communicate installation plans for smart meters at least every 6 months, containing the begin and the end of the massive phase of installation for each area of interest. From January 2022 may be installed only second generation meters. An actual proposal of the Authority for Electricity, Gas and Water, ARERA, is that to the end of 2025 at least 90% of the meters have to be installed. DSOs with more than 100,000 points of delivery have to reach 95% of second generation meters installed on their network until the end of 2026. Further regulations are still, let's say, work in progress. Thank you all very much for taking the time to listen to this presentation, and have a nice day.
Hi, my name is Jørn Engberg, and I am working for a company called NTE, an energy company, where I work as a project manager and an IT architect. I started in the company in 2011, and the start of my work was actually planning of the architecture of the smart metering rollout and use of this data. I'm very thankful and grateful for being able to attend to this panel discussion, and also I have a presentation later of the project that I was a part of in earlier these years. Well, in this short presentation I will talk a bit about standardization, what we did at NTE, what we looked at, what we didn't finish, and also talk a little bit about how we can, what kind of standards there are, and how we can inspire people to use those standards, both the utilities and the youth. I will also talk a bit about the smart meter. So, let's go. What? Do we really need more standards? Don't we have loads of standards already? That's a big question. Do we need these groups that discuss endlessly this and that, never agreeing? Well, our world exists of a lot of standards, and yes, they take some time to make, but while making, they are also used. And if we didn't have any standards, things would be very different in this world. Just using this media I'm using now, just making a search on Google or any search engine is based on one of the most common and standards today, the HTTP and the HTML protocols and languages. If it weren't for those, I couldn't actually search for standards at all. And let's say the physical standards about contacts railroads, the width of a railroad, railway tracks. What if each station master or station head should decide the width of those tracks? Well, it would be a lot of trains. Well, it shows that we actually have a standard for the smart metering. It's called the Common Information Model, IEC 61968-9, and it addresses the advanced metering infrastructure. Well, it's old. I don't know how long, but it has been here for a lot of years, and it's constantly evolving, and it addresses the advanced metering infrastructure and the meter, how to interact with the meter, what kind of components do we exchange with the different systems and kind of normal utility has. And it's very well defined, but is it up to date? Is it really up to date? That is a big question. Is it suitable? Well, that's also a big question, because things change very fast in these days. In my project, or our project at NT, we used this standard for the exchange of information, because there were no other standards that were actually ready. So instead of making a standard for the information exchange between our collection, or our headend, and our systems, because if we want to build that, it's an enormous, huge job. So we started with this standard, and I think maybe some of it has been changed to our need, but the standard is in the framework. So it's absolutely a standard that can be used for exchange of information, and it's supported by a lot of vendors today. So the vendors we talked to, they didn't actually support it when they started, but the standard is so well formed that it's easy for people that know the context. It's easy for them to get into it quick. So the big question is, do we need to search more, or do we need to make another one, or is it suitable to use this one and maybe try to use it the way we need, and where there are commonalities that we share. Yeah, so if we have a standard, how can we inspire for energy efficiency, or the use of those standards to the benefit for us all in this area, and maybe also for us all in the community? Well, I think first of all, the availability of standard APIs, application programming interfaces, and information models are of big essence. Without those, you will start on scratch, and that's too difficult, I guess. So I think the business has to make use cases that, for example, universities and of course the companies themselves and vendors can look at, and there are a lot of use cases already in place, but maybe try to make use cases specifically for the young people that's moving into our business now, and things like gamification, comparisons, everything that is contest is interesting. Savings is always interesting, and so these kind of use cases that motivates the youth, the young academics to program and to analyze data. Also, of course, internal support for internal processes. There are a lot of use cases there, which is actually very interesting. Ground earth failure, lots of how use of the energy. There are enormous amounts of use cases that we can actually present for the developers and the data scientists, and which also will inspire them. The analysis of energy use and flow, for example, very interesting for many academics. Also try to think in new ways like hackathons, which is a short and efficient way to inspire and motivate developers, analysts to make a product or a prototype. And you can invite broadly and give them access to these APIs and data storage, and they will play with it and make things that you didn't know could be made. We did that at NTE, and it was very interesting. We had a contest. There were several groups working on different use cases that they could choose among, and we had very good results with that. Of course, the big issue is how to take it further and actually use it. And one of the projects that came out, or the prototypes that came out of our hackathon, was actually used now. So also prototyping, internal and with vendors, try stuff, fail again, try once more. You will succeed at last with different kind of projects and prototypes, and use those agile methodologies that one use in the programming environment now. That's very exciting, and it's very interesting for people in our business to learn also, if we haven't already. And we must talk to the youth. They are curious. The youth are the coming energy business. So it's very important to inspire, and to inspire you will have to have standards, you will have to have APIs, you will have to have data, and of course the standards is beneath all this. So the standards, they are built on commonalities, and the commonalities are a lot, and it's defined in the infrastructure. But what are not the commonalities? Well, presentation of information, speed of deliverance, business models in this new energy landscape, extra functionality. These are the differentiators, and these are also exciting to look at. So, and maybe they are not the things that come out of it's not only consumption, it's a lot of other interesting data coming out of the smart meter and the infrastructure as a whole. Yeah. So the smart meter is a boring thing in our homes that just measures active and reactive power. Well, it does more than that. As you know, it can measure power quality levels, interruption, last gasp, ground fault analysis can be done, magnet detection, removal of the shield cover, measurement and distribution of load flow levels. And it has the opportunity to update remotely, and remote configuration, push and pull technology for events. Yeah, there's a lot of stuff going on in the meter with lots of measurements, and then it can provide the network company, the utility, with the information about last mile, last radial information, position fix, net loss, balance control. So there are there's a lot of different use cases that we can come back to. So the smart meter is not boring. It has actually a lot of sensors, and you can play with it. But it all depends on the standards. Thank you very much. So that was a short, very little technical information about standardization. But I'm more into the motivation of using the information that comes out of the standards. So with that, a nice picture from an area where I live. See you.
Hello, good morning. This is Inigo Berganza. I am the chair of the technical working group of the Prime Alliance. And today I would like to provide an overview on how the Alliance is committed to driving the standardization process for the benefit of smart metering markets. Prior to start, I would like to thank the organizers of this event, Mandana and the team at Smart Grid Forums, for the opportunity and also the very interesting topics that they are proposing today. I am going to touch on 4 elements that explain the position of the Prime Alliance with regards to standardization of AMI and smart grid markets. And by the end, I hope you will get the idea that the whole purpose of the existence of an association such as the Prime Alliance is actually to promote standardization in the AMI and smart grid sectors for the benefit of the market participants, that is ourselves. So I will start by providing an overview of the drivers and motivations that led to the creation of the Alliance and that still today makes new members want to join our initiative. I will then elaborate on the actual results of our work and how they became technical specifications that have, for the most part, turned into global standards. Then I'm going to touch on real experiences to highlight the benefits of standardization in a global market. And finally, we'll present the main ideas of our roadmap for the coming future. So, the Prime Alliance is an industry association with global reach, which was originally set up back in 2019 by 8 founding members, then formally registered in year 2012 as a non-profit association headquartered in Brussels according to Belgian law, and is currently formed by close to 70 members from all regions, Asia, Africa, the Americas, Europe, and Australia. The Alliance is open to any member that wants to participate in fostering AMI standardization, very diverse and independent from one single company or group of companies. And after 10 plus years of existence, we can say it's a stable association with visible position in the market. For reference, below I'm showing the logos of the 15 so-called principal members, the ones that are part of the board of directors. And there you should be able to identify 6 utility companies from 4 different countries, 5 of the most recognizable smart metering and AMI system vendors in the world, and 4 large global chip technology vendors, which in the end provide the basis silicon for all AMI network devices to function properly. The main driver for the 8 original companies to come together and form an industry association, even when some of them were competitors back in 2019, was the need that they saw in promoting a truly open solution for the then nascent AMI market in Europe and elsewhere that would enable real interoperability and interchangeability for the upcoming massive rollouts and the associated business cases. I would say these 2 key features of interoperable and interchangeable solutions were considered prerequisites for a healthy and competitive ecosystem that in turn would allay concerns from utilities about the risks and cost effectiveness of embarking in massive AMI rollouts. Being unencumbered by patents and a royalty-free approach was from the beginning a commitment of all of these members. So a decision to come together was taken in order to develop and use those solutions to support smart metering and smart grid deployments through 4 main activities. First, provide an open forum for the creation of protocol and technical specifications and standards, initially leveraging the experience that existed in the area of power line communications. Second, accelerate demand through a sponsorship of the market and user education programs. Third, encourage and promote broad and open royalty-free industry adoption and widespread use, and to protect the needs of consumers and increase market potential, for example, through uniform conformance test procedures, and processes that ensure interoperability of products and systems implementing the specifications adopted by the Alliance. Coming to the technical specifications themselves, they are developed under a framework in which first the whole membership of prime stakeholders provide market requirements, new ideas and lessons learned as feedback. This is then assumed and filtered by the board of directors who decides on a roadmap. And ultimately, there is a permanent technical working group that entertains open technical discussions, provides technical content and drafts specifications and compliance testing documents. And this technical working group has obviously a very diverse and heterogeneous membership. So the detailed work is usually carried by specific focused task forces, which are organized not very differently from the traditional OC model of layers. So there is a task force that deals with the physical layer issues, another one for convergence with application layers, etc. The first result of the work of the Alliance after some initial drafts was version 1.3 of the prime specifications, which covered the PHY and MAC layers, the lower layers of a standard protocol for power line communications, or PLC, that enables data to be transmitted between sets of smart meters at fixed locations and data concentrators, usually located next to the medium voltage to low voltage transformer of that particular area of the low voltage grid. Within a couple of years, the spec has been standardized by the International Telecoms Union, which is a global standards body that depends on the United Nations as G.9904, and also became part of the IEEE standard 1901.2 entitled Standard for Low Frequency Narrowband PLC for Smart Grid Applications. Now, the current version of the specs is version 1.4, which improves a number of aspects. And beyond that, the Prime Alliance released back in 2019 a DLMS COSEM companion specification called the Prime COSEM Profile, since most of our utility members employ DLMS COSEM as their choice for interoperable metering data exchange at application layer. And some of them were appreciative of a COSEM companion that could be flexible and at the same time tailored to be used over Prime PLC networks. Also, all the above specs have an associated compliance and certification process provided by independent laboratories that is defined and maintained by the technical working group. The latest version of the Prime PLC specs, version 1.4, allows for most robust performance and node availability in all kinds of grids, overhead, underground, short or long lines, which are found globally. This is thanks to previous experience of Prime version 1.3 in all type of scenarios. It allows binary point-to-point data rates of up to 1 megabit per second if the full bandwidth is used. And this is expected to cover the needs of AMI and low voltage smart grids for the foreseeable future. The frequency range extends to what basically all international regulations would allow for low frequency PLC applications, that is up to 500 kilohertz. It also supports applications that use IPv6. It is backwards compatible with the existing Prime version 1.3 networks, so the transition can be made seamless. And true to the commitment of the Prime Alliance with openness and the creation of a market of interoperable products, all the materials, the specs plus a few white papers, are publicly available at no cost. In terms of which has been the success level and the experience of the Prime specifications in the past years, I would provide a quick timeline and some numbers, starting with year 2010, in which the original specification was tested with small numbers of elements from different vendors. So only the successful execution of those tests, interoperable tests, led to the release of the specifications. And year 2011 saw the first massive deployment start in Spain in a rollout that ended having 9 different smart meter vendors deployed through successive yearly or 2-yearly competitive bids. In 2012, the first Prime PLC pilot took place outside Europe, that was in Australia. Also, a number of additional utilities in Western Europe started deployment of Prime networks, often tied to national mandates for AMI. 2013 saw the start of the first massive Prime rollout in Eastern Europe. In that case, it was in Poland. And in 2014, some projects started in Brazil and a number of countries in the Middle East region. By the end of the year, there were 5 million prime meters deployed and working worldwide. In 2015, the 10 million prime meter milestone was reached. 2 years later, we saw the first prime network installs in African countries, such as Egypt, Ghana, and Djibouti. And by the end of 2019, there were already more than 20 million prime meters deployed all over the world. This was also coincident with some European rollouts achieving the stage of maturity or even completion. Some takeouts I would like to share about all this experience throughout the years. You can see a map of the different countries where prime products, hence specifications too, have been used. The list, by the way, is not exhaustive. In terms of lessons learned, it is very clear for the Alliance that the whole approach of standardized and interoperable products has been vindicated, and it is attractive to the market. Because of that, it's a valid idea for future product generations, and we intend to somehow have it granted while the obvious technology evolutions come to us in the future. Needless to say, competition in the market has come with advantages in the cost effectiveness of products and systems. That is a value much appreciated by utilities. Similarly appreciated is the value proposal for utilities that through a standardized COSEM application on top of an interoperable PLC network that is privately owned, they can ensure total control and management of their own costs. They can modulate the pace at which deployments evolve, diminish technology risks, and provide for the privacy and cybersecurity that their customers demand. It is clear through Prime and also through similar initiatives that interoperable narrowband PLC has succeeded in many different geographies and has the potential to keep doing so. It is, however, important to consider the ecosystem around. Beyond the pure connectivity, there will be MDC and MDM systems, usually solutions provided by established market players, and standards should not be forgotten there. For example, in the Prime Alliance, we worked years ago to endorse and make publicly available specifications for a solution requested by utilities to use standard protocols such as FTP and web services based on XML that would enable these technologies to be used for interoperable exchange between data concentrators and central systems. With regards to the roadmap, in the Prime Alliance, we foresee an expansion of our traditional scope. If we start from the bottom, there are already use cases that are well known related to AMI requirements in previous years. There is an architecture that is mature and well tested with different application layers. And very importantly, there is a Prime ecosystem with optimized silicon and the certification processes that currently ensure seamless interoperability among vendors. Based on that, we see that the future will bring different options for connectivity. From the left, the last version of Prime specs, version 1.4, will allow enhanced features for mostly AMI deployments with increased speeds and robustness that cater for the need of very diverse scenarios. But the possibility to leverage radio frequency, RF, that is wireless connectivity, on top of the PLC itself to achieve 100% coverage in all possible scenarios is something becoming more and more attractive that Prime has decided to address. And also uniquely so, we do not constrain ourselves to the usage of low-frequency PLC, but are committed to the so-called broadband over power line, or BPL technology, to cater for potential data rate needs in the megabits per second. This will allow for full low-voltage grid automation and specific use cases, as will be briefly discussed. Achieving interoperability throughout these various forms of connectivity will provide utilities in the coming years with the most cost-effective tools to ensure satisfactory provision of services such as in-home service demanded by distribution customers, plus the future evolution of grid services such as automation, smart electric vehicle charging, etc., and AMI near real-time interactions. Touching on these last two initiatives of the Prime Alliance, the Hybrid Prime specifies the ability for a Prime network to dynamically decide for each point-to-point local exchange of data between usage of Prime PLC or unlicensed wireless, as specified by IEEE standard 802.15.4, standard for low-rate wireless networks. The RF frequency bands supported depend usually on the region, be it the Americas or Europe, Middle East, and the upcoming specs which are in final draft stage, intends to cover all main markets. There will be real hybrid prime pilots starting very soon, and we are seeing growing market interest such that hybrid solutions may become default for deployments in markets that are nowadays less mature. Secondly, Prime BPL will standardize the use of PLC in the range of several megahertz for the AMI and smart grid markets. In order not to reinvent the wheel, a specific task force inside Prime Alliance identified and thoroughly tested a state-of-the-art existing standard, G.9960 series, that defines, again, the PHY and MAC layers, the lower layers, for a BPL solution used to communicate nodes inside homes. Our idea is to be based on that existing, proven and open technology, ensuring that true interoperability can be achieved among current and future products, and guaranteeing that the specific requirements for the smart grid and AMI scenario are met, while having a common interface to any upper layer being used. Prime BPL is of a specific interest inside the Alliance to German utility E.ON and a certain ecosystem of vendors around, but we feel that the interest will grow in the future. So thank you for your attendance. Thanks again to the organizers of the event for the hard work. I hope this was useful for anyone interested on the perspective of the Prime Alliance regarding AMI standardization. And please feel free to follow us on this web link below. Stay safe and thank you very much.
Right, okay, welcome everybody. Thank you so much for all of your presentations. So we have quite a number of questions from the audience and I'm going to go through them in the order that they were presented to us. And then we should have a few minutes at the end as well for some panel debate and some questions between the speakers themselves. So let's start at the beginning with Tony. Tony, we have a question for you from Brian Finkel at Analog Devices. And Brian asks, does standardization discourage technology innovation, do you think? For example, from meter suppliers, would be interested in your point of view as both a standards expert and also working for a technology supplier for AMI.
Yeah, sure. It's something I hear an awful lot of in my day job. And I can see the point that everybody's making. If you standardize absolutely everything, what's left for innovation over the top of that? But of course, there is a level at which standardization does make sense. There's no point in having 15 ways to measure electricity, for example, or defining metrological accuracy in lots of different ways, because otherwise nobody really knows what they're getting. So there's kind of core ways of standardizing things, even to communication technologies. There's no point in having 15 different proprietary ways of communicating simple data that everybody gets. I mean, without standardization, it could be argued that it would be too difficult to innovate over the top of multiple proprietary specifications rather than using a core set of standards that everybody can lean on and then innovate over the top of. I mean, classic examples were mentioned today in the presentations: HTTP, HTML, TCP, UDP, you know, and a whole bunch of other alphabet soup that sits within the IT world. Without any of those things, I mean, nobody would be able to innovate on the web. Nobody would be able to create innovative applications that run over those protocols. If we move into the devices world, things like Bluetooth and Wi-Fi, you know, I don't need to mention, you know, how valuable those have been in terms of the peripherals, the mobile devices environment. And without those standards being in place, nobody would be able to stop at the airport, buy a mouse. You know, you can buy a £10 mouse or a £50 or £60 mouse. It doesn't make any difference. You know that it's going to work with your PC. You don't have to worry about reading all the technical specs and analyzing lots of different specifications to figure out that it's going to work. But you can't deny that there's been so much innovation in that mobile devices environment that hasn't been inhibited by standardization whatsoever. In fact, it's encouraged that innovation within the concept of standardization. And true as a meter supplier as well, if we move back to AMI, we look at supporting standards like DLMS COSEM, which was also mentioned in presentations today, provides a standard fundamental set of building blocks that you can then use in order to define a common language and a common data model, while it doesn't inhibit you whatsoever in defining exactly what you want in terms of the exchange of data between a client and a server or between devices. It's a way of thinking about it like the standard provides you a set of ingredients to make a cake, but it doesn't define how you make the cake. It's up to you what ingredients you put in the cake, but everybody who eats the cake will be able to tell immediately exactly what ingredients you've used in order to make it. But that innovation with defining what ingredients you want to put in your cake or defining what data objects you want to put in your model still allows you to innovate without managing to standardize things so to the point of not being able to define an application that is both innovative and standardized.
Yeah. You'd almost say that standards are essential for innovation at scale, couldn't you?
Yeah. Absolutely.
Yeah, great. Thank you, Tony. We have a question for Peter from Willem Strabbing at ESMIG. And Willem says, what communication standards are you using? And do you have suggestions for the standardization process regarding P1 and S1?
So when we look at the P1 data, I think this is easiest. So it's basically the data coming up until a sampling rate of a second. There, the P1 ports of the digital meters, they have the DSMR 5.02, I think, standards, where the S1 at the moment that we implemented it was fairly new in Europe, and there, to my knowledge, we didn't have a view on it back then, and it's still also an open question now. There's also little documentation on the S1 port, which makes it also very difficult for us to read it out and to interpret the data. So it was a little bit seeing what comes in and just trying to interpret it, what it exactly means. What I also find is that we definitely saw not only a strong need for the standardization of the onboarding procedure. Is what you currently see is that all the P1 ports are by default closed in Belgium, which makes that when you want to install a device, first you need to ask the end consumer to open officially this P1 port via an online application of the DSO. This takes, let's say, 48 hours, and then you need to couple back to the installer, who can then come and then install the P1 dongle devices to be able to collect the data. So from a consumer experience point of view, it's also important to work on standardized procedure that increases the consumer experience and doesn't need as much as different steps from opening the port to contacting the installer, etc., and that we can have a unified procedure also for installing this equipment. And this is from a practical point of view also very important.
Thank you, Peter. So, Andreas, we have a question for you, and it's from Brian Finkel at Analog Devices. Are different types of meters required for chain 1 and chain 2 communication? How is it determined which customers will use chain 1, PLC A band, versus chain 2, PLC C band?
So the meter is, for every customer, is the same meter. There is only the difference in the communication way. Chain 1 is for the communication with the DSO, and chain 2 is only for the in-house communication, so for the in-home devices for the customers. So this is the main difference, because the second generation smart meter in Italy is the same for everybody. So there are, for huge distributors, there are, or for there is in general, there is no difference between the meters. So every meter is able to communicate in chain 1 and in chain 2.
Nice. Okay. So, another question for you, Andreas, and this one is actually from Inigo, one of our panelists. Mm-hmm. And Inigo asks, how does the 169 megahertz work? Base stations do already exist, or will have to be deployed anew?
So in Italy, they already exist. It's a normal radio frequency that in Italy is already used for gas meters. So in Italy, there is no problem to use this 169 megahertz radio frequency. I don't know how the situation is in the rest of Europe. So if this channel is, let's say, free for other use.
Okay. And Inigo also would like to know, Andreas, on top of the PLC in chain 1 and 2, which is the application layer 2nd gen will use?
On top of the...
On top of the PLC in chain 1 and 2, which is the application layer 2nd generation will use?
In this case, I have to look up, so sorry.
Okay.
I have to look up, so.
No problem. Inigo, did you want to ask a supplementary question?
Yeah, just my interest, Andreas, was simply to understand if you guys plan to use, for example, a DLMS COSEM layer, both for the exchange in chain 1 versus the DSO, and maybe perhaps even with the customer, or you are not thinking that in that option, and you're, for example, reusing, I understand, the application protocol, which was not DLMS COSEM from the 1st generation.
So no, the 1st generation applications are totally deactivated, so there will be only the 2nd generation layer to use. So
okay.
Only the power line communication will be used for this.
Okay, wonderful, thank you. Well, we have 3 or 4 more minutes, and I'd like to encourage the panelists, if you have any questions for each other, now's the time to put those across. Please raise your hand if you have a question for any of the other speakers. Yes, Inigo.
I certainly do like to have the opportunity of Tony being here. In his many roles as that he described, I also know that he's been historically very active with regards to the DLMS COSEM. As you correctly noted, this has been mentioned as probably, perhaps from the application perspective, the oldest initiative in the AMI world towards interoperability back in the 90s. What is, in your view and in your expertise, the new borders, the new future evolution, and where will DLMS COSEM go in the coming years? Which are the application or the features that you still think that it will need and evolve to?
Sure. There's a lot of things that are currently on discussion within the user association, and in the interest of full disclosure, I'm also chairman of the board of directors for the DLMS User Association as one of the roles that I play within standardization. So at the moment we're looking at applications that are kind of adjacent to the metering application. Clearly there's a lot there at the moment within all types of metering. We've got electricity, gas, water, heat metering. Anything that can be defined within the utility space is already defined within the COSEM data model. And looking forwards, there are things that could quite easily be defined within that COSEM space that are using either existing objects or very slight changes for new objects, such as the communications between smart meters and EV charging units, for example, could be something that is something that could be considered as adjacent. Looking at talking to other appliances, maybe looking at other use cases like smart meter profile development and that sort of thing, to enable the story of interoperability to be more easily digested by people who are just meeting DLMS COSEM for the first time. So there's lots of innovation that's already going on there with those kind of new applications, and for the use of legal metrology via split meter application, which is already well defined within WellMech and in the world of legal metrology, but is something that maybe not quite as well defined in standards today. I mean, if you look at the Italian cross-section of standards, already there are DLMS COSEM applications used there for talking to in-home displays and remote displays and that sort of thing. Is a very, very well-defined structure of standards based on the application layer of DLMS, and a lot of innovation has already been going on within the CHIG to use DLMS in different ways, which of course the DLMS User Association loves to hear these great stories and success stories using the standard that, as you say, has been around since 1997 when it first started. It's a great place to innovate, and maybe it's been seen in the past as quite parochial and stuck around electricity meters, but certainly I think as the world goes on and as the two worlds of the kind of the slower moving utility environment, more risk averse and more stable utility environment moves to join with the IoT and consumer goods environments, then all standards that are operating in that space need to become a lot more flexible and need to become a lot more friendly to interacting with other standards outside that sort of vertically integrated silo environment. And the DLMS UA absolutely sees this, and it's the direction it's heading.
Okay, great, thank you, Tony. Well, I think we've arrived at the end of our Q&A session. So thank you all very much for your presentations and for your answers to those questions. Really appreciate that. We're now going into a 30-minute break. And again, I'd like to encourage you to make the most of the online networking tools, connect with each other, hold some video discussions, and we'll see you back for the next presentation at 11:45.